Okay, let's continue. Last class we have talked about we need the big idea or big tool to analyze the algorithm. If we just calculate the or plus all the time together, you will find you can never have a result. So we need have a more clever way to do the analysis. That is asymptotic analysis. So it will ignore the machine dependent constant and look at the growth. And we need some notations. Notation means symbols, and we need the symbol to help us. So let's take a look at the asymptotic notations. The first one would be the theta notation. Sometimes we just call it the big theta notation. So what does this theta notation do? It's pretty simple. It's just drops the low order terms and ignore the leading constants. Drops the low order terms and ignore the leading constants. For example, we have this statement: 3 times n cubes plus 99 n squares and minus 6n and plus 4068. So if we want to use the theta notation to express this statement, what would be like? So if we drop the low order terms, that means the constant doesn't matter, so we just drop it, and the first order, like the one order, this minus 6n, doesn't matter, we just drop it, and the second order means the n square, we drop it, and finally we just left the highest order terms and ignore the leading constant. Here's the 3, we ignored it. So with the theta notation, this expression would be equal to theta n squares. Actually, the thinking is pretty simple, because you just think when the n is big enough, like the most important part about this expression is just the highest order, right? The n squares will be much larger than the n cube or the just n, no matter what the leading constant is, when the theta is when the n is big enough. So that is theta notation. Just drops the low order terms and ignore the leading constants. Okay, for example, how to use I'll give you an example to show you how to use the theta notation and why do we need the theta notation. So, for example, we have two statements like tn1 equal to 9999 n square plus like 888 n and plus 777. And another one is the just the n cube, just n cube. So if we do not have the asymptotic notation, then it's hard for us to compare like these two algorithms, like which one is faster, which one is slower, because if you look at it in a mathematical way, that will depend on these leading constants. if it's just the same leading constant, for example, the n square or n cube, you can easily compare which is faster. But how about the leading constants always change, so that will take us a lot of time. But if we have the theta notation, so this t n1 is just equal to what? To theta n square, right? We just drops the low order term and drops the ignore the leading constant, so it's just n cube, theta n cube. And the second one would be theta n, oh sorry, just now it's theta n square, and now it's theta n cube. So if as n approaches the infinity, means n approaches the infinity, so what would these two algorithm, who is fast, who is slower? The theta n square algorithm always beats eventually the theta n cube algorithm, right? Always beats, no matter what these leading constant words, they'll always beat. Okay, so that's a good point of the asymptotic notation. Okay, so as n gets bigger, means as n approaches infinity, it doesn't matter what lower order terms, like these numbers, no matter it's 10,000, a million, or a billion, it doesn't matter. Okay, and no matter the low order is plus, whether it plus the n square or not, or what number is leading constants, it doesn't matter. The theta n square algorithm will always win. So even if you run the theta n square algorithm on a slow computer and run as or theta cube on a faster one, the result won't change, right? The theta n square will always win. So let me draw a picture to show you what will happen. It would be, I draw here. So here is the x-axis should be the n, and the y direction should be tn. Okay, yeah. This might be the theta n square, and here's another one for theta n square, n cube. So there's always a crossing point, and we call it n0. So when n is larger than n0, the theta n cube will always cheaper than the theta n cube. So that is the theta notation mean. So that doesn't change the results about the hardware. Even no matter if you run the algorithm on a supercomputer or just a normal laptop, that won't change the results. The theta n square will always win. Okay, so and the only thing is sometimes the n0 is so large. The error is n0 is so large, so that's why sometimes the software engineering are still interested in some slower algorithm. That means they focus on this part. So even as the asymptotic view, some algorithm will eventually win, but the n0 is too large. That is probably the computer are not big enough to handle the n0. So so they were interested in this part. That means uh, uh, they will use the slower algorithm to solve some problem. So it's not always the mathematical or the asymptotic. Sometimes you need your engineering view to see what's the real problem is. Okay, that's Cedar notation. So the greatest thing about the asymptotic notation is that it ignores the affection of the hardware. It satisfies our issues are able to compare to both the relative and absolute speed. So it's not about the speed or speed of the computer or the machine. It's just about the algorithm itself. It's just about the growth, how the speed will change as the n approach the infinity, how the speed will change. So it's a combine of mathematics and engineering. This is like just what I have said. If the n0 is so large, that you probably will eventually choose some slower algorithm. That doesn't matter. We don't always look at it as a mathematical problem or look the question as the asymptotic way. Sometimes we need the engineering way to solve the real problem. Okay, so that's about the theta notation, and that's some one thing to tell us how to ignore some details again. And one more thing we need to know is how about the upper bound we wanted, right? We discussed it before, like we need the upper bound because only upper bound is guaranteed to the user. So we need another notation to describe the upper bound. That is the O notation. Sometimes we just call it the big O. Big O. That's the O notation. We call it big O sometimes. Of course, there's still the small O, but we don't use that a lot. We use the big O. And what is the big O mean? From the mathematical way, it should be like this. If they are the positive constant C, and the n0, such that when the all the n is larger or equal to the n0, and the Tn is less or equal to C times Fn, then we can call the Tn equals to big O Fm. So if you just read this thing like this, probably most students won't understand the what they're really talking about. Again, that's I call it. It's the textbook language or the academic language. It's not our language. Our language is just use a picture to draw it. It will be much clearer. It should be like this. This direction is the n, and this is the time where t. You can see t, right? So there's a point that is the n0, that is a positive constant, and every n larger or equal to n0, then the Tn, if the Tn is here, then the C Fn should be here. Like if the n, when n is larger or equal to n0, I mean the right part, this part, and the c times Fn will always larger or equal to Tn. So that is the c Fn is the what we call the upper band. Right? So how about this part? Less or equal less than n0. We don't care, and we don't know. Actually, we don't know about this pair. How this line will change, where they cross. We don't know, and we don't care. We just know if this n0 exists, and every n larger or equal to n0, the c times Fn will larger than the Tn. That's enough. We call it the OFN. So it's the upper bound of Tn. And that's enough for us. So that is the big O, or the O notation. And also there's the omega notation. That's about lower band. That's a notation we do not use that much. We mainly focus on the big theta and big O. But you still to know the what is the omega notation mean? It's about the lower bound. In this picture, that should be a line like this, and this is the omega notation, and it's about the lower bound. The lower bound, as I said before, is not a guarantee, so it won't help us a lot. But in the future, if you learn some like advanced data structure, or some like an algorithm analyze course, in the future course there might be some part about the lower bound of an algorithm. That's another course. That's a totally another topic. So we don't use this a lot, omega notation. But you see to know what's it about. So just read the textbook, the section 2.1. And let me make sure. Yeah, the chapter 2, 1.1 section on the textbook. So read this part about the omega notation. So the most important to us is the big theta and the big O. So if you don't understand in the mathematical way, just look at the picture where easily understand why we call the big O is the upper bound. Okay. So what do we need to pay attention to when use the big O? So our textbook should have some bad example, like bad style. What is that? Is to contain the is to include the constant or the lower order term inside the big O. For example, like this, Tn equals to big O 2 times n square, or Tn equals to big O n square plus n. So that is a bad style. Why is that? So right now you need to combine the big theta and big O. So the combined two will give you, that's the leading constant. We can ignore the leading constant, and we can just drop the lower term. So what's the right way about these two statements? So the correct form for both parts should be Tn equals to O, big O and square. So the leading constant doesn't matter, and the lower order term doesn't matter. This is the correct form. So that's what we need to pay attention when we use the big O notation. Okay. Okay, then there are some rules about using the big O, the notation. So first one is let's assume if the T1 equal to big O FM and T2 equal to big O GN, then how about when we need to plus them together, T1 and the Tn, what the result would be? Do we need to calculate them one by one? For example, let's assume if the T1 is equal to let's say 5 times n to the fifth and the 3 times n to the 3, and we can also plus n and plus 9,999, and assume the T2 equal to 2 times n squared plus n, we could still use n, then plus 888. So how to calculate the T1n and T2n if the T1n and T2n is this? Do we need to calculate the result? Like, it really depends this calculate do we need to plus these two and then get a result? No, we don't need to. So based on these rules, if you use the big N, then the T1 is equal to 1. It's big O n to the fifth, right? You just drop the low orders and ignore the leading constant, and these two, the T2n is also the big N, a big O n to n squared. So if you plus them together, then the then the lower order will also just dropped, right? So you don't need to actually calculate. So you just need to and the times T1 times T2 is also the same. You don't need to actually calculate it. You just need to, if the T1n plus T2n, so you just choose the max of these two, that's enough. Okay, because the lower order doesn't make any change to the result. And if you need to calculate the T1 times T2, the results just times the 2 big O. That's enough. You don't need to actually calculate the T1n times the T2n. So that is the rule for you to calculate. Okay. And nextly, in this slide, I will give you some typical growth rate about the all the big O, all kinds of growth rates about the algorithm and its order, which one's faster, which one's slower. So pay attention to here the constant 2100 or 2000 or 100. We usually use the big O1 to express a constant. Then you can say as n became larger and finally approached infinity, what are the O1 and the log n? Which one is faster? it should be O1. O1 is faster, right? No matter how large the constant is, no matter how large the constant is, the log n will eventually larger than the constant, than O1, right? So I draw a line like the log n below the O1 in purpose to show you, to try to get your attention. Like, no matter how large the constant is, it will always like faster than the log n. So the typical growth rate, which one is larger, which one is smaller, is that you should know. That's the fast one is the constant. We usually write like O1, okay, and then it's the log n, and the On, and the n times log n, and the n squares, n cubes, and the 2 to the power n, and the n factorial. So you will see the 2 to the power n is pretty slower, and I will give you a timetable about that. This is a timetable about the different growth. Like the color is the input number, the size of the input, and the row is a different type of the algorithm. We will see the big O. And the unit about this is the mu s means the mu seconds. That is our right now. That will equal to 10 to the minus 6 second, and we still have the ms. That means the microsecond. That is the 10 to the minus 3, okay, second. And we have the minutes, that you should know. And you have day, we have day here. That means day. Okay, and we still have the YR means year. So you will see, for example, the first column, the Fn equal to n. So the time, the actually running time will be increasing, right? Will be increasing when the input number is larger and larger, and the time will increasing. And this is a module like calculated by a model computer. That computer is can do billion operations per second. Can do billion operations per second. So, and basically about this part, the left part is what we wanted. So it were not that slower. It's just milliseconds or just minutes at most. So, but this part, the right part, is we don't want. Okay, especially this one, the 2 to the nth. You will see like this part. So the input number is just 100. If your algorithm is the were described as O2 to the n, and you were it will take you the 4 times and 10 to 13 years. That's years to get the results. So of course we cannot see the result, and after so many years, I'm not sure the earth, the sun is still there, right? It probably the whole universe was just gone. So that is a very horrible like the speed of the, or terrifying speed about the algorithm. It's just like the story about the king and the chessboard. It's kind of like they play a bet with some farmer or something to play the chess, and if the king lose, the farmer just asks the some rice, and the first in the first grade is the 1 grain of rice, and the second is 2, and the next is 4, and next is 8. So basically it's 2 to the n's. And how large is the chessboard? It's the 8 by 8, so it's 64. Then what would be the all the number to plus them together? So that's 1 plus 2 and plus 2 to the 63, right? So some people just calculate it. It's a huge number about all the grains. They calculate the how many the number is, and to calculate how many grain would be 1 kilo. 1 kilo rice. So the total number would be nearly 300 billion ton. So the total weight of this number rice would be 300 billion tons of rice. So that's a huge number. So if you found a really good algorithm to solve like a problem like the anyone never solved it before, but the speed would be big O to the n, then you probably never see a result. So we should evolve our algorithm is like this speed to the power of n. So we like the on and the log n and n log n, and the n square and n cube is probably we still can accept it. It depends on the input size, but if it's still the speed is still lower, like the n to the fourth above, it probably too long. You see, the input is just 10,000, and the n's fourth will be take 100 a day. That's 1/3 of a year. That won't help to us, right? So that's the warning table. So you should know about the which one is faster, which one is slower, and which one we should to evolve. That's a typical growth about the algorithm. Okay. Okay. After we have the notations, we have the tools. Let's look back. Let's look about the same example. How to calculate. So if we don't have it, we need to make assumption like how much time where this sentence, this code will spend. So but after we have the notations, let's take a look at what will things change. First we'll take a look at the first line. It will the code will do sum equal to 0. That means you put 0 into the sum. So we can call it a 1 unit time. Okay, it's a 1 unit time. It's slower or faster depend on your hardware, depend on your computer. So if we use the asymptotic ways, that's we didn't count the exact time. Okay, we didn't exact time. We can call it 1 unit time. So it's a constant time. Whatever is what long is a constant time. And the same thing is to the line 4. It's the same. It's a 1 unit time. Okay, and the key part is the line 2 and line 3. And in line 3, with an analysis before, it actually like did 4 times of calculation. It did twice time the multiply, and 1 time plus, and 1 time equals. So that is we can call it 4 unit time, 4 basic time. Okay, and it's inside a for loop, and the loop is executed n time. So the total is 4 and execute n time. The total should be 4n. Okay, and the very similar thing is the line 2. This part I equal to 0, it just execute like 1 time, and this part I less or equal to n, it execute the n plus 1, and the I plus plus it execute n times. So totally it's the 2 times n plus 2. Then we just add them together, so the total time is 6 times n plus 4. Right, that means this is 1, this is 2n plus 2, and this is 4n, this is 1. So totally is 6 times n plus 4. And we have learned the notation theta and the O, so we know this function is a big O(n). The time will be related with the input size. Okay, it's a big O(n). And in terms of the asymptotic notation, you will find lots of shortcuts that can be taken and without affecting the answer. For example, we didn't care about the how many times, for example, for the line 3, we did not care how many times the unit about, like in our example it's I cube, or you can still, and even you can plus I or plus I square. That doesn't matter. That is from the asymptotic view. That is a constant time, right? It's a O(1). So we just think about the how many times the loop will do. So actually it is silly to count precisely whether it is 2 units, like it's I plus I, or it's 3 units, or I plus I plus I, something like, or it's 4 units, like I squares, and then so it is silly to do that. So when we have the asymptotic notation, as long as the whole sentence is a constant, you can treat it as like O(1). So that give us several general rules about the asymptotic notation. Okay, and the first rule would be the we call it for loops. So as I said before, we don't care much about inside the loop. We care about how many times the loop will execute. So running time of a for loop is at the most running time of statements inside the for loop, like most of the running time inside the for loop. And times here, times means multiply the numbers of the iterations. For example, we have a for loop like this: for I equals 1, or I less or minus than n, and I plus plus. So what here inside the loop to exactly execute, actually we don't care. As long as it's some basic operation, we can call it O(1). Then what important to us is the number of the iteration, that how many times this loop will execute. So that's the most important to us. So that's for loop. Okay, rule 2 is a nested for loop. Nested means we have multiple layer of the for loops, the outside layer, the inner side layer. First thing was analysis from excuse me. We will analyze the nested loop from the inside to outside. And about the total number would be the time of the statement and multiplied by the product, the size of all the for loops. I mean, that also we care the most about how many times the basic statement will execute. Again, it's another example about the nested. That's 2 layers, the outside, the inner side. So the basic statement is the k++, and the time of the basic statement is just a constant, right? No matter how fast or how slow your computer is, it takes some constant time. It's not relevant with the n, so it's all 1. And the total time is we will multiply the size of for loop. So for the inner side of the loop, it will exceed like n time, right? And the outside will another n. So for this part, the total number would be big O, what? N squared. Okay, the two layers and the total size of the loop would be n2, and the basic statement is a constant time, so the final result would be big O, n squared. Okay, that's rule 2. And rule 3 is about the consecutive statement, and that is simple. You just add them together. Just like the rule we mentioned before. You have T1 or T2. How to calculate the time, like T1 plus T2. That is we leave the maximum of the two statements. So you just add them together and keeps the maximum is what we need. So again, this is example. We have like consecutive statement. Like the first part, you will say how long it is. It's a big O(n), right? So it's just one layer of the for loop, and it's n times. And the second part is a nested for loop. We have 2 layers of for loops, so it's the n squared. And the total number, you just plus them together, and that is the maximum of these 2. And the result should be O, big O, n squared. Okay, that is the consecutive statement. And the last one, rule 4, is about the if-else, about condition. And again, it's very simple. Like we have the form like this: if condition, and if the condition is true, we just execute the S1 statement. Else, if the condition is false, then we'll execute the S2. Then how to calculate the total number of the if-else statement? So the total number will never more than the running time of the test. So the first part is test, and plus the larger of the running time of S1 and S2. That means you need to this part, like condition part, and plus the max of the S1 and S2. So that's 4 basic rules about the asymptotic calculation. Okay, how to analyze some program fragment. You should know about that. Okay, so that's 4 basic rules you should know. Okay, I will give you some exercise about this chapter. So one thing is about the recursive procedure. Recursion means like you call yourself again and again. For example, we calculate the n factorial. You should know the symbol, right? N factorial. N factorial is equal to like n times n minus 1 and times n minus 2 until 1, right? So if we calculate the how to use a program to calculate the n factorial, you will use the recursive or recursion. So you will say if you calculate the n factorial, actually it's the n times the n minus 1 factorial, right? And right now we need to calculate this part. Then n minus 1's factorial just equal to n minus 1 and plus times the n minus 2 factorial. So that where recursion will happen. So you will call this part. For example, we have a function like calculates the factorial. So you will just call yourself again and again and again. That is the recursion. So what about the time? What about the big O right now? So if the recursion is happen, how to calculate the big O? Okay, try to spend time to think about this part. How to calculate the big O if the recursion is happen. Okay, so and some more exercise is just in our textbook at the end of the chapter 2. So just think about the 2.1 and 2.6 A and B. Okay, that's not a really hard problem. The exercise will be harder and harder when they are at the end part of the exercise in our textbook. So the first few questions would be pretty simple. So and try to spend some time to solve it. And you don't need to hand in, and we don't have the condition to hand in or check your exercise like every times. But I highly recommend you doing this exercise. It will help you understand your study, and it also some may show up in the exam. So I mean after every chapter I will give you some exercise, and some of them will show up in the final exam. So try to spend time to solve these problems. Okay, and that's all for today. Let's see you in Thursday.